Alright, in this video lecture, I'm going to discuss about the open circuit and short circuit tests on a practical transformer. Uh, you have to basically understand the equivalent circuit that we discussed in our previous lecture, and also how to refer the impedances from secondary side to primary side and primary side to secondary side. You must be known to understand this lecture properly. So I would like to revise what I have covered in my previous two lectures regarding the equivalent circuit and referring to one side, impedances referring to one side, before I start this lecture. So let me go to my first lecture on the equivalent circuit. Right. So I hope you remember the equivalent circuit that we discussed. And this is the primary side of the transformer, and this is the secondary side of the transformer, and we consider this part as the ideal transformer, where we have no any kind of losses. So when it comes to the practical transformer, the winding resistance are there, the leakage reactance will be there, some flux will be leaking out, and then core losses like hysteresis loss, eddy current loss will be there, and also it will consume some energy to initialize the magnetic field. For that we need certain amount of current. So represent all these practical parameters. What we did, we add some components to this ideal transformer, right? So this one R1 represents the primary winding resistance, and X1 represents the leakage reactance, and this parallel branch is actually representing the core losses. So this R naught is representing the eddy current loss and hysteresis loss, and X naught represents the initializing magnetic current. And similarly in the secondary side, R2 represents the winding resistance, and X2 represents the leakage reactance, and ZL is the load, and this V1 is the primary source that we are supplying the power energy to the transformer. So so then we, in my next lecture, we discuss about, let me show you the other lecture, next lecture. It is about the equivalent circuit referred to primary and the secondary side. So here we said that even though we have now so far studied about equivalent circuit, still the two sides are isolated, or they are just inductively coupled, right? So to do the calculations as normal circuits, we have to make these two circuits into one, which is single circuit, which is conductively coupled by using impedance transformation, right? So that means what we are going to do, we are going to refer all the impedances on the secondary side to the primary side, and consider it as a single circuit, right, through impedance transformation. And so there we assumed an ideal transformer, and then we showed that V1 over I1 for this ideal transformer, where V1 is the primary voltage and I1 is the current, primary current, and V2 is the secondary voltage and I2 is the secondary current, and ZL is the load. And remember, this is an ideal transformer, right? So in that case, we could prove V1 over I1 is equal to A squared Z del, right? So basically V1 over I1 means when you look from this side into the transformer, V1 over I1 is basically the impedance that you see. So we can derive it as A squared Z del. So we can just forget about the secondary side, and we can just assume that there is an impedance equal to A squared Z del, like this, right? So this is now equivalent to this circuit where V1 and I1, when you apply V1 it will draw same current I1. So the impedance here is A squared Z del, so which is equivalent to this setup. So this is called referring the secondary side impedance to the primary side, right? So what we have to do is basically multiply it by the square of the turns ratio. Turns ratio is n1 over n2, or we can say it is primary number of turns in the primary side divided by number of turns in the secondary side is A. So you multiply the whatever the impedance on the secondary side by A squared, and then you can put it in the primary side. So this is what we call the referring secondary side impedances to the primary side. So in that way we can replace this uh, isolated two circuits into a single circuit having the equivalent impedance like this, right? So now knowing this thing, we can go to our practical transformer equivalent circuit, where you had these primary winding resistance and leakage reactance, secondary winding resistance and secondary leakage reactance, um, and then the core losses are represented by this parallel branch, right? So this is the circuit. So now here we have the ideal transformer, and this could be considered as the load that we have, right? Therefore we can transfer these two uh, components, the resistance and the reactance components, into the primary side using the previous a method of transferring the impedances. So or else we can we can transfer the primary side impedances to the secondary side as well. That is also possible, which can be seen from the next slide, this one. So here this is equivalent to either this one, where you have transferred secondary impedances to the primary impedances just by multiplying with A squared. I will enlarge it for a clear visibility. See, this is A squared JXS is the new impedance in the primary side, and this is the winding resistance, A squared into RS, the secondary one. So it comes as RS dash here. This is coming as XS dash. So this is what we call referring to the all resistances and reactances have been referred to the primary side. The similar thing you can do the other way around as well, where all the primary side impedances you can refer to the secondary side impedances. In that case, you are referring the primary side impedances to the secondary side. All reactances and resistances and reactances have been referred to the secondary side, like this, right? So that is what you have to basically understand about referring the impedances to either side. Okay, so uh, So so this is how it will look like when you refer the secondary side impedances to the primary side, right? So this is xs dash means the secondary reactance referred to the primary side, then it is actually a squared into xs. This is the winding resistance of the secondary coil referred to the primary side. Rs dash is equal to a squared into rs. So remember here A is the turns ratio, NP over NS, right? Okay, right. So like this you can refer to the second side as well. Finally, these parameters of the transformer equivalent circuit like RP, XP, XS, RS, and this RC, XM, all these parameters um, can be derived uh, or rather found by using several tests. They are called open circuit test, short circuit test, winding resistance test, and transformer ratio test. Basically, open circuit test will give us these core parameters RC and XM. Then short circuit test will give us RP, XP, the winding resistance and the reactances, leakage reactances of primary and the secondary. And then winding resistance test can also measure the winding resistance, and the transformer ratio test will give us the A value, NP over NS value. Right. So as these two are more direct tests, we will now look at open circuits and short circuit test, right? So when we refer these impedances from one side to the other, the equivalent circuit will look like this, right? So here this is now the, instead of the transformer, now you can use this equivalent circuit, right? So this has referred the secondary impedances to the primary side. And then to make this equivalent circuit more simpler, you can shift this parallel branch to the input terminals here like this, and then these two you can easily add. So this is actually an approximation. This is adding some error, but still for practical calculations that is not a very big error, because the main reason is this XM and R naught are very high impedances, so this I naught current is very small, so I1 will not change very much if you shift it to the initial point here. Therefore and it will simplify the circuit so that we can add these resistances and reactances which are in series. So from here onward, as the equivalent circuit for a transformer, we are going to use this model, right? So now I think we can come to the today's lecture, that is how to find these parameters using uh, open circuit and short circuit test. Right. So so it is possible to predict the performance of a transformer at various loadings by knowing all the equivalent circuit parameters. You might think why we are doing all these tedious tasks to find about these parameters. You know, when you know these parameters, you can calculate voltages and currents easily for different loads. This is because when a transformer is on no load, that means when you have not connected any load to the secondary, uh, you will get a certain voltage at the secondary terminals. But when you connect a load to the transformer, this voltage changes, mainly because it is drawing some current from the secondary side, and this current uh, itself will generate uh, an opposing magnetic field on the secondary coil, right? And this flux is again linking to the primary side, and it has some impact on the primary side as well, right? Therefore it will reduce the magnetic flux on the primary side, and then the back EMF will be reduced, and due to that more current will flow into the primary coil. So like that, as we discussed earlier, when there is a load on the secondary side, there is an impact on the transformer, right? Therefore the voltages, the voltage basically at the secondary terminals will be changing, right? So it depends on the current that we are drawing from the secondary coil. So therefore the transformer calculations are not that easy. It is little bit complex. To make it simpler, we use this equivalent circuit, and if you know these parameters that we discussed before, then the the simpler circuit, the equivalent circuit, which is having only one side, right? Because everything on the other side is referred to the one side. Therefore, we can do the normal. You can apply the normal theorems to analyze the single side one circuit, right? So if you know the load, then you can calculate the currents, the other currents and the voltages easily, right? That is why we are going to find out the parameters of a transformer using open circuit and short circuit test. So these circuit parameters are supplied in terms of open circuit and short circuit test data of a transformer. So let's first look at the open circuit test, or rather it is called no load test. Open circuit means no load is connected to the secondary side. It is open, right? The shunt branch parameters, that is the core losses, iron or the core losses, are determined by performing open circuit test. So we can find the RC and XM values of the equivalent circuit um, using the open circuit test. Since the core loss and the magnetizing current depend on the applied voltage only, right? It is mainly uh, the decided by the core loss, and the magnetizing current is mainly decided by the applied voltage only, right? Not by the current, and practically unaltered by the load current. So there is no impact on these parameters by the load current. Therefore, even any any load is not connected at the secondary, still the values can be found from the open circuit test. Hence, to get these parameters, um, rated voltage is applied to one of the windings, keeping the other windings open, right? So what we are going to do now, we are going to apply rated voltage on one side of the windings, and we keep the other side open circuit. Here it is open circuit, no load is connected. This is just a voltmeter connected to measure the output voltage. But here uh, we are going to apply the rated voltage. You know, for a transformer, there is a rated value that is normally given as kVA value. Or if it is a small transformer, we just say input voltage is 230 volts and output voltage is 24 volts, 12 volts, 48 volts, like that. So that is called the rated voltage. It is given in RMS value, right? So so in this test, normally we open circuit high voltage side. Generally, high voltage winding is it is written here. Generally, high voltage winding is kept open, and rated voltage is applied to the low voltage winding, right? So for example, if it is a 230 to 48 volt transformer, 230 side is called high voltage side, 12 volt side is called low voltage side, right? So in this test, in the open circuit test, what we do, we open the 230 side and apply uh, rated voltage, that is 12 volt, to the low voltage winding, right? uh, so when we do this, the current open circuit during the open circuit test, current flowing is about 4 to 5% of the rated current when the secondary is open, and when you apply rated voltage to the primary side, the current drawn by the transformer is very small, like 4 to 5% of the rated current, right? So then by using an ammeter we can easily measure that. Otherwise, you know, if it is 10 amperes, 20 amperes, 30 amperes, like that, we have to have a ammeter which is capable of measuring that big current. But in the laboratories we don't have such multimeters. Therefore, we open circuit the high voltage side and give a rated voltage on the to the primary side. Then the current will be small, so that we can measure it easily, right? That is the reason why we open circuit the high voltage side and applying the rated voltage to the primary side, because simply because it is measurable then. For example, here you have to measure the current by using an ammeter, and you have to measure the voltage by using a voltmeter, and also you have to connect a power meter to find the power taken by the transformer, right? So the circuit diagram to conduct this test is shown here. That is the circuit diagram. So now this is the low voltage side, which is we are applying the rated voltage, and the secondary side, high voltage side, is open circuit now, right? So when it is open, we say no load is connected, right? So it is open. So hence the current drawn from the source is called the no load current. It is called the no load current, and normally we denote it by I naught. If you remember the equivalent circuit, when no load is connected on the second side, this I naught is basically going through that parallel branch, right? So so that is called the no load current. Ammeter, this ammeter gives the no load current I naught, and voltmeter gives the applied rated voltage to the primary side, and wattmeter gives the input power to the transformer, which is actually V1 times I naught times cos phi naught. Um, this is the normal power equation Vi cos phi. So V is V1, I is the I naught, and cos phi is the power factor, right? And Vi values are in RMS values. So so with the help of these three readings, that is the voltmeter reading, wattmeter reading, and the ammeter reading, we can find the input side power factor cos phi naught, right? Um, Hence we can find IC. So IC will be I naught cos phi naught, and IM will be I naught sin phi naught. So if you know IC and IM, you can find R naught and XM, because we know the voltage across R naught and X naught XM, right? It's like this. Uh, so you are measuring this I naught because this side is now open. There is no current going through this side now in the equivalent circuit, because we have no load connected. So the current drawn by the transformer is basically I naught. So so you know I naught, and also you know the voltage, and also you know the power taken by, that is Vi cos phi value is also known. So Vi known, Vi cos phi known, therefore you can find cos phi naught. So if you know cos phi naught, then here this I naught is actually the current through XM plus current through R naught. So vector addition of these two will give I naught. So basically R naught is I naught cos phi naught, and the IM that is going through this one is I naught sin phi naught, right? So that is taken from the phasor diagram, which is shown here. So now the equivalent circuit for no load will be like this, because this part is going away as there is no load, and then this I naught is represented by this arrow here, this arrow here, which is the sum of I naught, and which is the sum of I think this is IC, IC plus IM, right? IC is the current going through R naught, and IM is the current going through XM. So I naught is basically IC plus IM, and IC and voltage is in phase, because IC is the current through the resistor, and this is an inductor, so it is perpendicular to the voltage, right? So this is the phasor diagram for that open circuit no load test. So then as I said, cos phi naught is equal to power divided by V into I, because P equals Vi cos phi naught. So from this you can find this particular angle phi naught, and then if you know phi naught, if you know I naught, you can find IC and IM. So IC is basically, if you know IC, then you can calculate R naught, because you know V1. So V1 over IC is R naught, and V1 over IM is XM, right? So in that way you can find these two parameters of the equivalent circuit by using the open circuit test. I hope it is clear. The same thing could be understood by using different methods. If you look at this diagram, where you are applying V1 here, R1 is here, L1 is here, and this is L naught and R naught, whatever it is, and the primary side. So so at no load, I naught is very small. When there is no load going on the secondary side, this I naught is a very small value, just to magnetize the core, right? And to indicate the eddy current and hysteresis loss, we are using R naught. So therefore the voltage drop across R1 and L1 is very small, because I naught is very small. I naught is the same current going through this one, and actually the voltage drops across these two can be neglected. So whatever V1 you apply here will be applied over here as well, right? uh, so across these two components, the same V1 we can assume by just neglecting these drops, right? Therefore we can consider the voltage across the shunt branch is still V1. Hence xm will be omega L naught, which is equal to V1 over Im, and R naught, which is equal to V1 over Ic, can be found, because we know Im and Ic, right? So we can show that the wattmeter reading is giving the iron loss as shown here. So the wattmeter reading is actually giving the core loss, the total loss. Um, so as there is no load, P out and I2 are 0, because there is no output power or output current. So as I naught is very small, power lost at primary, PR1 is also very small and can be neglected. So power lost at the primary also can be neglected, because these are very small currents going through this one. So therefore input power is V into I, V1 into I naught cos phi naught. Um, Alright, don't get confused with different notations here, because I have taken this from another video clip. Here WR is basically the wattmeter reading, right, which is equal to input power V1 I naught cos phi, and you know P input power is equal to the output power plus losses. And when we say losses, there are two types of losses, iron losses and copper losses. So iron losses mean the core loss, so it is represented by Wi here, and these are copper losses. Secondary winding copper loss is I2 squared R, but I2 is 0, so this part is 0. Primary winding resistance is R1, so it is I naught squared R1, because at no load primary current is I naught. And as I naught is very small, we are neglecting this as well. Therefore P naught is also 0, because there is no power, no current going on the secondary side. Therefore finally we get input power is equal to Wi, which is iron loss, right? So Pi equals Wi. So Pi is again the wattmeter reading. So from the wattmeter reading we get the iron loss, right? So so different people are using different notations, and here through open circuit you can find out IW is actually the working current, which I have used the same notation in my first lecture on transformer equivalent circuit. It is actually the the current drawn by the core losses, that is eddy current loss and hysteresis loss. So I naught is actually divided to Im and Iw. So you can find these two, and then from these two you can find R naught and L naught, and also the iron loss, that is Wi, right? Okay, now we will look at the short circuit test, or rather impedance test. So for that you can consider the circuit here. So you short circuit the secondary side, and then you refer all the parameters to the primary side, x2 dash and r2 dash, and then you apply a voltage here, right? So so suppose the input voltage is reduced to a small fraction of the rated value, and the secondary terminals are short circuited, right? So you apply a very small voltage here while short circuited in the secondary side. The primary voltage is gradually increased, right? Now this voltage is gradually increased till the rated current flows in the winding. So in the primary winding there is a rated current now, which can be found from the kVA rating and the primary voltage. So you know the rated current, so you can increase this primary voltage until rated current is flowing on the primary winding. That voltage will be very small because the secondary is short circuited now. So very small, maybe of the order of 5 to 8% of the rated voltage. A current will circulate in the secondary winding as well. Due to this current, there will be a current going on the secondary, but it is short circuited. So it will be the rated current for the secondary. That current again will be the rated current because primary is carrying rated current. Since a small fraction of rated voltage VSC is applied to the primary winding, here we have applied a very small voltage, the flux in the core, and hence the core loss will be equal to VSC squared over R naught. The core loss will be V short circuit squared over R naught. When we say loss, actually loss is happening on the resistance R naught only. So the voltage applied across this one is VSC, so it is VSC squared over R naught. It's very small because VSC is small, right, compared to the copper losses. Copper losses due to R1 and R2 dash. So it is basically I2 dash squared R1 plus R2 dash, right? And I2 dash is large. It is actually the rated value, right? Rated to full load current. So hence the magnetizing branch can now be eliminated from the equivalent circuit, because this the loss is very small in the core, because this is very small, but compared to the other losses that is happening on this one, the series branch, this can be neglected, so we can just eliminate the parallel branch or the magnetizing branch. Hence the power input on short circuit is dissipated as heat in the winding. So whatever the power you give here, input on the short circuit is dissipated as heat in the winding. So all the power will be dissipated here, right? The modified equivalent circuit would be as shown below. So this is the modified equation. So if short circuit is applied voltage to circulate the rated current I2 dash on the short circuit, and PC is the power input to the transformer. So the power value that we input to the transformer is PC. Uh, so we can write down this equation. ZSC equals V short circuit to I2 dash. Um, so then cos theta is PC over V short circuit into I2 dash. Therefore, you can find cos theta. And as you know, V short circuit and I2 dash, you can find ZSC as well, right? So then from these two, you can get the value R1 plus R2 dash, which is equal to Z short circuit into cos theta, and x1 plus x2 dash, which is equal to Z short circuit sin theta. So this way you can find the winding resistance, total winding resistance, and also the total leakage reactance. So this is the setup we are going to use. We have to use a variac. Variac means a variable voltage source, AC source, right? Because you need to apply a very small voltage when it is short circuited, right? So for that we use a variac, and then we use a voltmeter to measure the power, and a meter and the voltmeter to measure the current and the voltage. So this current on this circuit will be rated full load current, and this circuit will be rated secondary full load current. So the short circuit test would give full load copper losses, then equivalent winding resistance and the leakage reactance, voltage regulation. Voltage regulation is another parameter that we use to specify a transformer. So in this test, the low voltage terminals of the transformer are short circuited. Remember, in the open circuit, we open circuit the high voltage side. In the low or in the short circuit test, we short circuit the low voltage terminal, right? But remember, we have to use a thick wire because large current will be flowing. So the reasons for short circuiting the low voltage side could be given as the rated current on the high voltage side of a transformer is less than the low voltage side, and therefore we can measure this current with the help of available laboratory ammeters. Because it is normally a low current, and the current flowing here will be only 5 to 8% of the rated current, so we can easily measure that. And also greater accuracy in the reading of the voltmeter is possible, because when we use the high voltage side as the primary, the applied voltage is less than 5% of the rated voltage. So if we use the low voltage side, the voltage is small and 5% will be very small, so it is difficult to measure it accurately. But as we are using the low voltage side, sorry, as we are using the high voltage side as a primary, then the 5 to 8% is a significant value, so we can measure it accurately. right. So you have to remember these two reasons why we are short circuiting the high voltage side. Sorry, why we are short circuiting the low voltage side. Right. So we have to calculate the full load primary current using kVA value and the rated primary voltage. We can find the rated current. So in this test we have to allow rated full load current to flow in the transformer by gradually increasing the supply voltage. Then the both windings will carry respective rated currents, that is full load primary and secondary currents. So that is why it is actually called full load test, right? This supply voltage measured by the voltmeter will be very small, and this is because the voltage required to give rated current measured with ammeter in primary winding, while the secondary winding is short circuited, is very small. So if we now look at the equivalent circuit referred to the primary uh, that is used for this short circuit test will look like this. uh, so this is primary winding resistance and this is secondary winding resistance referred to the primary winding, and similarly the leakage reactances referred to the primary side, and this is the core losses. uh, the input power given by wattmeter reading will be equal to copper losses, as no output power is going out, right? Because there is no other power dissipating component in the output side. It is short circuited, and very small or negligible iron loss compared to the full load core losses. So so Wi, that is iron loss, is equal to actually V1 squared over R naught, as V1 squared is very small, this is small, so we can neglect that. And the copper losses will be I1 squared into R1 dash, that is this resultant resistive component. This is very large because rated current is going. So we can write down the equation now. Pi, the input power, is equal to the output power plus losses. So output power P naught, it is 0 at the moment because we have short circuited it, and the losses will be copper loss and iron loss. PCU is the copper loss, that is this one, and iron loss, this one. This is also negligible because it is very small. So finally whatever the wattmeter reading that we are getting is equal to the, that is input power is equal to the copper losses. So therefore the short circuit test gives the full load copper loss. So by using wattmeter reading and ammeter reading, and we can calculate R1 dash. So wattmeter reading is equal to the copper loss, it is equal to I1 squared into R1 dash. So as we know I1 squared and as we know wattmeter reading, we can find R1 dash. We can further simplify the circuit by removing shunt branch like this. So by using voltmeter reading and ammeter reading, we can find XL1 dash as well. Right, if you know R1 dash, you can find XL1 dash using voltmeter and ammeter readings. because V1 over I1 is equal to square root R1 squared dash R1 dash squared plus XL1 dash squared, the square root of this one, right? So when you know R1 dash, then you can find XL1 dash. From R1 dash and XL1 dash, we can find equivalent impedance referred to secondary side as follows. So by using these are actually referred to primary side, so you can find the values referred to secondary side, because values referred to secondary side is basically R1 dash over squared, which is actually equal to R1 over squared plus R2, and XL1 over a squared plus XL2 is XL1 dash over a squared, which is referred to the secondary side. So this is equivalent winding resistance referred to the secondary. This is equivalent leakage reactance referred to the secondary. So you know both R1 dash and XL1 dash. Also this is referred to the primary side, this is referred to the secondary side. Just wait, I think there is something wrong here. Just give me a minute. Okay. Right, so let me put it to the projector mode again. So now if you referred it to the secondary side, voltage V1 will be V1 over A, and this is the primary winding resistance referred to secondary. This is primary winding reactance, leakage reactance referred to secondary, and this is primary secondary winding resistance and the secondary winding reactance. So the total impedance here will be addition of all these four components. Right, so you can simply represent the total circuit like this then. ZL is the load. Right, in our case ZL is short circuited in the short circuit test. Right, so so in that case the voltage regulation is defined as V no load at the secondary minus V load at the secondary divided by V load at the secondary. So voltage regulation is basically giving us an idea how a transformer is giving a different voltage, or not the rated voltage, when the load is changing. So when the load is changing, how the output is changing is given by the voltage regulation. Normally if it is a high value, that means there is no much difference in the output voltage when the load is changing. Right, so it is actually measure of the quality of the transformer. Normally the output voltage should not be much dependent on the load. So that percentage is given like this. So mm, we no load voltage at the secondary is actually uh, I2 ZS dash is the voltage drop here, and V LS is the open circuit voltage here. So V no load voltage, V no load voltage is I2 ZS dash is the voltage drop over here plus the voltage drop over here is equal to the no load means then there is nothing connected here. So but when you connect the load here, what will happen, this voltage will drop. So so that drop is equal to this one, I2 into ZS dash. So when you connect a load, this is the value, the voltage across the load. So no load value means the addition of these two, and minus VLS is the when the load is connected voltage, and then VLS same here, and percentage. To take the percentage, you multiply it by 100. So so this parameter is called the voltage regulation. So if you can find Z dash, that is this value, then you can find the voltage regulation, right? Because you put that value here, and then you know I2 value, and I2 is the rated current, no? So and VLS is the voltage across the load, right? So so this is about the open circuit and short circuit test. So if you are doing it as a practical in the lab, by using the short circuit test, we can find full load copper losses. By using the short circuit test, you can find the full load copper losses, and also you can find the equivalent resistance and reactances of the windings, either refer to the primary side or to the this is primary side, this is the secondary side, and also you can find the voltage regulation. And then there is another parameter called the efficiency of the transformer. So when we say efficiency, it is basically comparing the output and the input. So if it is high efficient, output and input should be same, ideal case, but due to losses the output will be less than the input, so in that case the efficiency reduces. So electrical energy is transformed when a transformer is used, and losses occur as with all all transformations of energy. The losses in transformers have various causes. The iron core is heated due to the continual magnetic reversals, that is called iron losses. And then when a transformer is on load, the windings are heated by the current flowing through them, that is called the copper loss. And then the open circuit and short circuit test will enable us to find the full load efficiency of the transformer. So these are the two losses, iron loss and copper loss. So iron loss is basically I squared RC value, that is RC is the component that is representing the iron loss, or rather hysteresis loss and eddy current loss, which we measured using open circuit test, the power of the open circuit test. And the copper losses we found from the short circuit test, which is basically equal to I1 squared R1 plus I2 squared R2, which is equal to the short circuit power drawn by the transformer. So therefore this is referred to the primary, and this is referred to the secondary. Sorry, this is the absolute values R1 and R2, but if you refer it to the primary or secondary, you will get something like this, right? So efficiency P is P out over Pi. Then P out is actually the VRMS IRMS into cos phi. So input power is P out plus losses. Sorry, here VRMS IRMS cos phi is actually the kVA rating into cos phi. And then if you come to input power is output power plus losses here. Output power plus losses here. So losses will be mainly iron loss and the copper loss. Iron loss you can find from open circuit test, copper loss you can find from the short circuit test. So then kVA ratio you already know, into power factor divided by kVA rating into power factor, that is P out plus iron loss and the copper loss at full load. So efficiency basically depends on the power factor of the load, that is this one, of the load and the load as winding loss depends on the current. This copper loss is dependent on the current. So far given load, so for a given load, for a given power factor, efficiency can be calculated. So if you consider for the full load means when the output is short circuited and the current rated currents are flowing on the both the windings, we can find the efficiency using this formula, because these two values we are this one is measured through short circuit test. And the winding resistance, sorry, iron loss, we are using the open circuit test. So this is the wattmeter reading at the open circuit test. This is the wattmeter reading at the closed circuit test. Right. So So in a simple diagram we can show the power flow through the transformer. You give some input power and iron loss will happen due to the core losses, and then copper loss, winding loss will happen, and then you get a smaller amount as the P out. And then efficiency is P out over P in. You can calculate it like this as a percentage. So to check the performance of the device by comparing the output with respect to the input, you use the efficiency parameter. The higher the efficiency, the better the system. So efficiency is output power over input power in this one. So these things you can we have already discussed about this one. So it's V2 I2 cos theta over V2 I2 cos theta plus PC plus PCU. PC is the core loss and PCU is the copper loss. So PC value you are getting from the open circuit test, PCU value you are getting from the short circuit test. And this is for the full load, right? So that is this one. And if the load factor is n, that means it's a halfly loaded or quarterly loaded from the full load, then we can derive another equation having the load factor. N is called the load factor, n into VA cos theta here over n into VA cos theta plus the core losses will not change due to the load because it is totally voltage dependent, and this copper loss actually had to be multiplied by n squared because it is I squared proportionate to I squared. So if the load is large, say double, then the power loss will be 4 times. So if X is the load factor, then you can calculate the efficiency at that load using this formula. This should be output power. So referring to voltages on the secondary, you can write it as X into V2 I2 cos phi 2. So to get the maximum efficiency, efficiency of transformer along with the load and the power factor is expressed by this equation. So if you divide this by I2, is V2 cos phi 2 over V2 cos phi 2 plus Pi over I2 plus I2 squared, sorry, I2 into RES. This is the winding loss. So the value of the terminal voltage V2 is approximately constant. Therefore the V2 cos phi 2 is a constant value. Thus for a given power factor, the transformer efficiency depends upon the load current I2. In the equation 1 shown above, the numerator is constant and the transformer efficiency will be maximum if the denominator with respect to the variable I2 is equal to 0. If you differentiate this with respect to I2, if it is 0, then that means the maximum value of efficiency. So so you differentiate the denominator with respect to I2, then you if it is 0, that means it will be 0 when the efficiency is maximum. So so you can get V2 cos phi 2 um, uh, that is this part, right? uh, P I over I2 I2 RES, this should be 0. Actually there should not be a equal sign here. So so this is a constant, so derivation is 0, and this is Pi over I2 squared when you differentiate it, and this is RES, so should be 0. That means I2 squared RES should be equal to Pi. So Pi is actually the short circuit, sorry, open circuit power, that is iron loss. This is the short circuit power, and that is the winding resistance, power loss due to winding resistance. Therefore, when the copper loss equal to the iron loss, we get the maximum efficiency. So thus the transformer will give the maximum efficiency when their copper loss is equal to the iron loss. Right, so efficiency maximum will be this part, you can put it as 2 pi because the PC and pi are same. So from this equation you can find particular I2, that is the secondary current, to get the maximum efficiency. So it will be given as when you find I2 from this one, you will get I2 as Pi over RES square root. That you have to find from this equation by differentiating this one with respect to I2. Okay, so so if x is the fraction of full load kVA at which the efficiency of the transformer is maximum, then the copper losses will be x squared PC PC, where PC is the full load copper loss, and iron loss will be Pi. So for maximum efficiency, x squared PC should be equal to Pi. Therefore, output kVA corresponding to the maximum efficiency will be x into x full load kVA. So if you put the value of x from the above equation here, then we get a maximum efficiency is P1 over BC into full load kVA. So efficiency will be full load kVA into with square root of iron loss over copper loss at the full load. So finally, if you look at the practical transformers, the output voltage depends on the type of the load. If the load is resistive, the voltage drop is very small. That actually you are getting from this efficiency equation. this is iron loss. Iron loss is something due to conductance, and copper loss is due to the winding resistances. So if it is totally resistive, then the output voltage drop is small, but the voltage drop with an inductive load is greater than that with the resistive load. See, this is for resistive load, this is for inductive load. So voltage drop is larger for inductive loads, and then for capacitive the output voltage rises slightly. So large capacitors should not be connected to the main supply directly, because it will increase the output voltage of the transformer. So with that we end this lecture on the full load, or rather short circuit and open circuit test, and how to find the parameters. So if I just summarize what we have discussed so far, by using these two tests we can find the equivalent circuit parameters of a transformer. So the two tests are called open circuit test and short circuit test, and if you know the equivalent parameters, then you can easily calculate voltages and current for different loads. So from open circuit test we can find the core loss parameters, that is resistance, the resistive component which represent the eddy current loss and hysteresis loss, and the inductive component is representing the initial magnetizing current. So these two can be found by using open circuit test, where you open the secondary and apply rated voltage on the primary side, and then you may, by measuring current and input power, you can find core loss parameters. And using the short circuit test, you short circuit the secondary and set the primary voltage to a value which will let the rated current flow on the primary side and the secondary side. So and then you measure the input power. So this input power basically represent the copper losses on the transformer. So other two parameters that you can get out of these two tests is voltage regulation and efficiency, transformer efficiency. So voltage regulation is basically the quality of the transformer. That means quality high means it can maintain the output voltage independent from the load, how much it can maintain the output voltage independent from the load it is taking. So it is like V no load voltage minus V load voltage divided by V load voltage is called the voltage regulation. And then efficiency means the ratio between output power and input power. That also you can calculate from the results of the tests here, because the efficiency you can measure by the output power divided by output power plus the losses. The losses will be mainly due to copper loss and the iron loss. So copper loss is getting by the short circuit test, and iron loss is or the core loss is taken by the short circuit test. So with these values you can find the efficiency. And also we said that we can calculate to get the maximum efficiency. We found that the colos and copulas should be equal. Colos and copulas should be equal. So to get the maximum efficiency, you can find uh, the other parameters like the load current, the load power factor, or the winding resistances, core losses, etc. Right? And then at last we said when the load is resistive, the voltage drop is very less, and when it is inductive the voltage drop is larger, but when it is capacitive the output voltage go a little higher. There is no voltage drop, but the voltage will goes up. So with this I finish the transformer section, and next day when we meet again we can do this two test and find the parameters of the given transformer. And if you have any doubts, any questions on this lecture, you can ask them through the WhatsApp. Thank you very much.